The space between stars will kill you in ways you haven't imagined. Not quickly, like Hollywood suggests, but through a combination of physics so hostile that your body's basic chemistry becomes your enemy. What most people call empty space is actually one of the universe's most sophisticated death traps. Let's start with what you think you know about vacuum. You've probably seen the movies where someone gets sucked into space and instantly freezes or explodes, or both. None of that happens. The reality is stranger and far more unsettling. In 1966, a NASA technician was testing a spacesuit in a vacuum chamber when something went catastrophically wrong. The pressure dropped to what you'd experience at 36,000 meters altitude. He had 12 seconds before losing consciousness. His last memory, the saliva boiling off his tongue. Not hot boiling, mind you, just evaporating because there wasn't enough atmospheric pressure to keep it liquid. He survived because they repressurized the chamber in 27 seconds. But that incident revealed something crucial about the void between stars. It's not the temperature that gets you first, despite space being nearly 300 degrees below zero. It's not even the lack of air, though that's obviously a problem. It's the absence of pressure itself. Your body right now is experiencing 14.7 pounds of pressure on every square inch of your skin. You don't notice it because the pressure inside your body pushes back equally. Remove the external pressure, and that equilibrium shatters. The water in your tissues, your blood, your cells, it all wants to become gas. Not because it's hot, but because nothing is holding it in liquid form anymore. But here's what makes interstellar space particularly fascinating. It's not truly empty. When you look up at the night sky, the darkness between those pinpoints of light seems like pure nothingness. Scientists thought so too, for centuries. They called it the ether, then the void, then just empty space. They were all wrong. The average cubic centimeter of interstellar space contains exactly one atom. One. To put that in perspective, the air you're breathing right now has 30 million trillion molecules in that same space. Earth's atmosphere at sea level is 30 quintillion times denser than the space between stars. The best vacuum humanity has ever created in a laboratory still has about 10,000 atoms per cubic centimeter. We literally cannot make anything as empty as natural interstellar space. And yet, that one atom per cubic centimeter adds up. The Milky Way contains so much interstellar space that these scattered atoms account for 5% of our galaxy's total mass. 5% of hundreds of billions of solar masses just drifting between the stars. Most of it is hydrogen, the universe's simplest and most abundant element. About 10% is helium. Everything else, all the carbon and oxygen and iron that makes planets and people possible, represents less than 1% of what's out there. This isn't just trivia. This matters because interstellar space isn't passive. It's not a stage where cosmic events happen. It's an active participant in how galaxies evolve, how stars form, how elements spread through the cosmos. And it's trying to kill anything that ventures into it. The temperature situation is more complicated than you'd expect. When someone asks what the temperature of space is, they're asking the wrong question. Temperature measures the average kinetic energy of particles. But when you only have one particle per cubic centimeter, that measurement becomes almost meaningless. The cosmic microwave background, the leftover radiation from the Big Bang, gives space a baseline temperature of 2.7 Kelvin. That's minus 270 degrees Celsius, minus 455 Fahrenheit. But here's the twist. Some regions of interstellar space are hot, incredibly hot. The coronal gas that fills 20 to 60% of the Milky Way reaches temperatures of 1 million to 10 million Kelvin. How can space be both frozen and millions of degrees hot? Because temperature in a vacuum doesn't work like temperature in air. Those few atoms might be moving incredibly fast, carrying enormous kinetic energy, but there are so few of them that they can't transfer that heat efficiently. An object in interstellar space doesn't heat up or cool down through contact with surrounding particles. It radiates energy directly as infrared light. This creates bizarre scenarios. A rock floating in certain regions of interstellar space could be bathed in million-degree plasma, but the rock itself might stay relatively cool because those plasma particles are too sparse to transfer their energy effectively. The rock would mostly gain or lose heat by absorbing or emitting radiation. It's temperature by isolation rather than temperature by contact. The interstellar medium exists in multiple distinct phases, each with its own personality. The cold neutral medium hovers between 10 and 100 Kelvin and has the highest particle density of any interstellar region. This is where new stars are born. The warm medium runs 5,000 to 10,000 Kelvin and comes in both atomic and ionized varieties. Then there's the hot ionized medium, filling the largest volume but containing the smallest fraction of mass because its particles are spread so thin despite their extreme temperatures. These phases don't mix casually. They maintain their distinct characteristics because of an inverse relationship between temperature and density. Hot gas expands until its pressure matches the cold gas surrounding it. Cold gas compresses under its own gravity. The result is a cosmos that's not uniformly distributed, but structured into regions with wildly different properties, all of them hostile to human life in different ways. The densest regions are the molecular clouds. About 1% of the Milky Way's disk volume consists of these dark clouds, where particles crowd together at densities of 10,000 to 100,000 atoms per cubic centimeter. That's still a better vacuum than anything we can create on Earth, but by interstellar standards, it's positively crowded. These clouds are the nurseries where gravity can finally overcome the tendency of matter to drift apart. Compress them enough, heat them enough through that compression, and you get nuclear fusion. You get stars. But between these stellar nurseries lies the true emptiness. Regions where you might find 0.1 atoms per cubic centimeter. Spaces so devoid of matter that they approach theoretical perfection as vacuums. And wandering through all of it, invisible but deadly, are the cosmic rays. Cosmic rays sound like something from science fiction, but they're terrifyingly real. They're atomic nuclei, stripped of their electrons, accelerated to speeds approaching light itself. 89% are protons, just hydrogen nuclei. 10% are helium nuclei. The remaining 1% includes everything up to uranium, the heaviest naturally occurring element. These particles carry staggering energies. The weakest cosmic rays pack about 1 billion electron volts. The strongest ever detected carried 100 million trillion electron volts. That's more energy than the most powerful particle accelerator humans have ever built. Where do they come from? Supernova explosions, probably. Maybe pulsars, those rapidly spinning neutron stars. Possibly active galactic nuclei. the supermassive black holes that anchor galaxy centers. We're still not entirely sure. What we do know is that they're everywhere in interstellar space, constantly bombarding anything that ventures there. The energy density of cosmic rays in interstellar space averages about 1 electron volt per cubic centimeter. That's comparable to the energy density of visible starlight. Interstellar space is as much defined by this invisible radiation as by its emptiness. And unlike starlight, which you can block with a thin sheet of metal, cosmic rays penetrate deeply. They slam into atomic nuclei, shattering them, creating cascades of secondary particles. They damage DNA. They destroy electronics. They represent one of the fundamental barriers to interstellar travel. A human traveling through interstellar space would absorb about 70 rems of radiation per year. The safety limit is 5 to 10 rems per year. That's without any shielding, admittedly, but shielding against cosmic rays isn't simple. Make your shield too thick, and the cosmic rays just create more secondary particles as they smash through it. The radiation problem doesn't have an easy solution. And then there's what happens if your ship is moving fast, really fast, close to the speed of light. At those velocities, even the sparse hydrogen atoms of interstellar space become a radiation hazard. Each atom you hit becomes a high-energy particle collision. The faster you go, the worse it gets. The dream of relativistic interstellar travel crashes against the reality that the empty space between stars becomes a lethal particle beam when you're moving through it at significant fractions of light speed. But perhaps the strangest thing about interstellar space is that despite being one of the best vacuums in the universe, it's not actually empty of chemistry. Molecules exist out there, complex organic molecules. As of now, radio astronomers are discovering about 4 new molecular species per year in interstellar space. How can chemistry happen when atoms are separated by meters or kilometers of emptiness? The answer involves those cosmic rays we just discussed. When high-energy particles slam into hydrogen and helium, they ionize them. An ionized helium atom can split carbon monoxide molecules. That creates ionized carbon, which can trigger chains of organic chemical reactions. Over millions of years, in regions where the density creeps up toward 10,000 atoms per cubic centimeter, actual chemistry emerges. Polycyclic aromatic hydrocarbons form. Amino acid precursors, the building blocks of proteins and DNA, assembling themselves in the darkness between stars. Interstellar space even contains dust. Not much, just 1% of the total mass, but enough to matter. These grains are tiny, a fraction of a micron across, roughly the wavelength of blue light. They're made of silicates, like beach sand, and carbon soot, like diesel exhaust. We know this because their infrared signatures match laboratory samples exactly. These dust particles dim the light from distant stars, making the universe appear less bright than it actually is. They also provide surfaces where atoms can meet and bond, tiny islands of solid matter in an ocean of near vacuum where chemistry can happen faster than it would in pure gas. The interstellar medium isn't static. It's not just sitting there waiting for stars to form. It's stirred by stellar winds, shocked by supernova explosions, heated by young stars, compressed by spiral density waves moving through the galaxy. Material cycles between stars and the interstellar medium in a grand recycling program. Stars form from interstellar gas, fuse hydrogen into heavier elements, then return those elements to space through stellar winds or supernova explosions. The iron in your blood was forged in a star that died before our sun was born, scattered into interstellar space, then gathered again into the cloud that formed our solar system. This is the environment that Voyager 1 entered in August 2012. After 35 years of travel, the spacecraft crossed an invisible boundary called the Heliopause, the point where the sun's influence ends and true interstellar space begins. The change wasn't subtle. The count of high-energy particles, cosmic rays from distant supernovas, jumped sharply. Low-energy particles from the sun dropped almost to zero. Voyager had left our cosmic neighborhood and entered the galaxy proper. What it found there surprised everyone. The plasma density was 40 times higher than expected. Interstellar space wasn't as empty as the models predicted. And Voyager detected something else, something nobody anticipated. Plasma waves, oscillations in the charged particles of the interstellar medium, creating what you might call the sound of interstellar space, though of course sound can't travel in vacuum. These waves ring at frequencies determined by the density of electrons around them. Higher pitch means more particles. Voyager's instruments picked up these vibrations, these ghostly whistles in the electromagnetic spectrum, revealing structure in what we thought was formless void. The spacecraft is still out there, still sending back data, though it's so far away now that radio signals take over 22 hours to reach Earth. It's traveling through a region of space that no human-made object has ever encountered before, measuring particle densities and magnetic fields and radiation levels in an environment that exists nowhere else we can access. Every measurement refines our understanding of what empty space actually means. And here's what we're learning. The emptiness between stars isn't simple. It's not one thing. It's a shifting mosaic of different densities, different temperatures, different levels of ionization and molecular complexity. Some regions are cold stellar nurseries. Others are superhot bubbles blown by ancient supernovas. Some areas are relatively dense with molecular clouds. Others approach perfect vacuum. The space between stars has geography, has weather, has an ecology of sorts where different phases of matter interact and transform. Understanding this environment matters for more than academic curiosity. If humanity ever ventures beyond our solar system, we'll be traveling through interstellar space for years, decades, possibly centuries depending on our technology. That journey won't be through empty darkness. It'll be through a complex, hostile, fascinating medium that's simultaneously one of the best vacuums in existence and a surprisingly active participant in cosmic evolution. The question isn't whether interstellar space is empty or full. It's both, depending on your perspective and what you're measuring. What matters is understanding exactly what's out there, what hazards it presents, and what opportunities it might offer. Because the space between stars isn't just the gap we have to cross to reach other worlds. It's an environment unto itself, with properties and behaviors we're only beginning to understand. And those properties start with something you wouldn't expect in the deadliest vacuum in the known universe: temperature. In the deadliest vacuum known to exist, where one atom drifts alone through each cubic centimeter of space, temperature becomes something alien. The baseline measurement hovers at 2.7 Kelvin, negative 270 degrees Celsius. That's the cosmic microwave background, the leftover warmth from the Big Bang itself, stretched and cooled by 14 billion years of universal expansion. Every point in space carries this ancient heat signature, This fossil radiation from when the universe was young and dense and blazing with primordial fire. But that's just the floor. The actual temperature of interstellar matter varies by millions of degrees depending on where you measure and what you're measuring. Some regions reach 8,000 Kelvin, others soar to 10 million. The hottest zones, heated by supernova shockwaves, achieve temperatures that would vaporize any material we could possibly construct. And all of this exists in what we call empty space. The paradox makes sense once you understand what temperature actually measures in a vacuum. On Earth, temperature indicates how vigorously molecules jostle against each other. Hot coffee has billions of water molecules bouncing around rapidly. Cold ice has those same molecules moving sluggishly, locked in crystalline structures. Temperature describes collective behavior, the average kinetic energy of particles in close contact. Interstellar space has particles, just not many of them. A hydrogen atom might travel kilometers before encountering another atom. When atoms are this sparse, temperature becomes a different beast entirely. Each individual atom might be moving incredibly fast, carrying tremendous kinetic energy. That's high temperature by definition. But with so few atoms present, there's almost no heat transfer, no conduction, no convection. An object floating in million-degree gas wouldn't heat up the way you'd expect because there simply aren't enough particles colliding with it to transfer significant thermal energy. You'd lose heat faster than you'd gain it. Radiation would be your primary concern, not the sparse hot atoms drifting past. Your body would radiate infrared energy into space, cooling gradually, while the occasional high-energy particle smacked into you with negligible effect. The vacuum itself can't transfer heat efficiently because heat transfer requires matter, and interstellar space barely has any. This creates zones of radical thermal variation existing side by side. Cold molecular clouds at 10 Kelvin sit adjacent to coronal gas at 1 million. The transition between them isn't gradual. You could cross from one to the other in relatively short distances because there's no medium to smooth out the temperature gradient. Each phase of the interstellar medium maintains its own thermal identity, separated from neighboring regions by density boundaries rather than thermal ones. The composition tells its own story. 70% hydrogen atoms, most of the rest helium. Everything else, every element heavier than helium, accounts for less than 1%. These heavier elements, carbon, oxygen, iron, silicon, came from stars. Stellar nucleosynthesis forges them in fusion reactions deep inside stellar cores. Then supernovas scatter them across space when those stars explode. Every atom of calcium in your bones was created in a star that died before our sun formed. The iron in your blood was forged in nuclear fire, blasted into space by a supernova, then gathered by gravity into the cloud that eventually collapsed to form our solar system. This chemical enrichment happens slowly. Early in the universe's history, only hydrogen and helium existed. The first stars formed from purely primordial gas. They fused hydrogen into helium, helium into carbon, carbon into heavier elements, building up the periodic table through successive fusion reactions until their cores filled with iron. Then they exploded, seeding space with the products of nucleosynthesis. The next generation of stars formed from slightly enriched gas. More supernovas, more enrichment. Generation after generation, the interstellar medium accumulated heavier elements. We're living in a chemically mature galaxy now. Our solar system contains about 2% heavy elements by mass, enough to form rocky planets and biological molecules. But that enrichment took billions of years and countless stellar deaths. The atoms that make up Earth and everything on it are the ashes of dead stars, scattered through space, collected by gravity, reformed into new structures. The interstellar medium contains these elements in all their forms. Individual atoms drift alone. Molecules form when atoms collide and bond. Dust particles aggregate from countless molecules. The medium has phases, distinct states that coexist in the same general region but maintain different properties. The cold neutral medium runs between 10 and 100 Kelvin. It has the highest density in the interstellar medium, which still means incredibly sparse by Earth standards. This is where star formation happens. Gravity pulls the gas together, compressing it until fusion ignites. The cold neutral medium serves as the raw material for stellar birth. The warm medium spans 5,000 to 10,000 Kelvin. It exists in both atomic and ionized forms, depending on local radiation levels. This phase fills substantial volume, but doesn't contribute much mass. It's the transition zone between cold molecular clouds and hot coronal gas. The hot ionized medium dominates volume, but not mass. Supernova explosions heat vast bubbles of gas to millions of degrees, creating expanding cavities of thin, scorching plasma. These bubbles can be hundreds of light years across, yet contain less total mass than a modest molecular cloud because the gas is so diffuse. Temperature and density maintain an inverse relationship. Hot gas expands, spreading out until its pressure matches surrounding cooler regions. Cold gas contracts under gravity, compressing into denser structures. The balance between these phases creates the complex ecology of interstellar space. Then there's dust. Just 1% of the interstellar medium's mass, but crucially important. These microscopic grains, smaller than the wavelength of blue light, form from silicates and carbon and ice. They're essentially tiny particles of beach sand and soot floating in space. We know their composition because their infrared emission spectra match laboratory measurements of sand and soot almost perfectly. Dust affects everything. It scatters and absorbs starlight, making distant objects appear dimmer and redder than they actually are. Nebulae look dark, not because they're empty, but because dust blocks the light behind them. Dust grains also serve as surfaces where molecules can form. In the frigid vacuum of space, two hydrogen atoms rarely encounter each other with exactly the right conditions to bond. But on a dust grain surface, atoms can stick, accumulate, meet other atoms, form molecules. Molecular hydrogen, water, carbon monoxide, even complex organic compounds assemble on dust grains before drifting off into space. The chemistry happening in interstellar space rivals anything in a laboratory. Over 200 different molecules have been detected through radio astronomy, with new species discovered at a rate of about 4 per year. Some are simple, molecular hydrogen, carbon monoxide. Others are complex organic chains, molecules with 10 or 15 atoms arranged in specific structures. This chemistry relies on cosmic rays. These high-energy particles slam through space at nearly light speed, ionizing atoms they encounter. An ionized hydrogen atom can react with molecular hydrogen to form the trihydrogen cation. An ionized helium atom can split carbon monoxide. Each reaction opens pathways to more complex chemistry. Polycyclic aromatic hydrocarbons form and transform through hydrogenation and oxidation. stepping along pathways that lead toward amino acids and nucleotides. The building blocks of life exist in interstellar space. Not life itself, obviously, but the chemical precursors, the organic molecules that could eventually assemble into biological structures given the right conditions. Some scientists argue that Earth's early organic chemistry might have been seeded by interstellar molecules delivered via comets and meteorites, though this remains speculative. What's certain is that interstellar space isn't chemically dead. Despite the extreme vacuum, despite the radiation, despite temperatures ranging from near absolute zero to millions of degrees, chemistry happens. Molecules form, react, break apart, reform. The medium has chemical activity driven by completely different mechanisms than terrestrial chemistry, but activity nonetheless. And then there are cosmic rays. These deserve special attention because they represent one of the primary hazards for any object traveling through interstellar space, whether it's Voyager 1 or a hypothetical future starship. Cosmic rays aren't rays, they're particles. 89% are protons, bare hydrogen nuclei. 10% are helium nuclei. The remaining 1% includes heavier elements all the way up to uranium. These particles have been stripped of their electrons and accelerated to tremendous speeds by supernova shockwaves, by active galactic nuclei, by processes we don't fully understand. They travel through space at significant fractions of light speed, carrying enormous kinetic energy. The energy range is staggering. Low-energy cosmic rays carry about 1 giga-electron-volt, comparable to what a small particle accelerator produces. The highest energy cosmic rays reach 100 million tera-electron-volts, far beyond anything the Large Hadron Collider can achieve. When these particles strike matter, they create cascades of secondary radiation. They knock atoms apart, produce gamma rays, generate particle showers. For spacecraft, and especially for human bodies, this creates severe problems. The radiation dose from cosmic rays in interstellar space runs about 70 rems per year for a stationary object. Humans can safely tolerate 5 to 10 rems annually. Beyond that, cancer risk rises sharply. Central nervous system damage becomes likely. Degenerative diseases accelerate. A multi-year journey through interstellar space without heavy shielding would be lethal. The problem gets worse at relativistic speeds. If you somehow built a spacecraft capable of reaching 10% light speed, the interstellar hydrogen itself becomes a radiation hazard. Each hydrogen atom you encounter hits with enough energy to produce dangerous secondary radiation. The faster you go, the worse it gets. At half-light speed, the oncoming flow of interstellar gas produces radiation levels that would kill crew within hours unless you had meters-thick shielding. This is the environment Voyager 1 travels through now, and will travel through for millennia. The spacecraft is hardened against radiation, but not designed for biological safety. It's measuring that radiation, counting particle impacts, mapping the intensity of cosmic rays as it ventures deeper into interstellar space. Every measurement refines our understanding of what any future interstellar mission would face. The radiation environment isn't uniform. It varies with location, with proximity to supernova remnants, with the local magnetic field strength. Some regions are relatively quiet. Others are radiation hellscapes, where particles rain down at rates that would destroy electronics and shred DNA. Understanding this variation matters enormously for planning any mission that would actually send humans beyond the heliosphere. But radiation isn't the only concern. There's also the question of what happens to a human body in vacuum. Hollywood has conditioned us to expect explosive decompression, instant freezing, bodies bursting from internal pressure. The reality is both less dramatic and somehow more disturbing. Exposure to hard vacuum causes unconsciousness in about 12 seconds. That's how long it takes for deoxygenated blood to reach your brain. You wouldn't freeze instantly because vacuum is an excellent insulator. With no air molecules to conduct heat away from your body, you'd cool slowly through radiation. You also wouldn't explode. Your skin is strong enough to contain your internal pressure, at least for a while. What would happen is ebulism. Water in your tissues would vaporize, not boil from heat, but from lack of pressure. At 0 atmospheres, water transitions directly from liquid to gas at any temperature. Your saliva would boil off your tongue. Moisture in your lungs would vaporize. Tissues containing water would swell as that water turned to vapor. You'd puff up like a grotesque balloon, though your skin would probably hold together. The timeline for survivability is shockingly short. Animal experiments suggest full recovery is possible if recompression happens within 90 seconds. Beyond that, survival becomes unlikely. Past 2 minutes, death is essentially certain. Your last conscious thought would come around the 12-second mark, right as your brain runs out of oxygen. You'd have perhaps 15 seconds of agonal gasping before unconsciousness, then another 75 seconds before biological damage becomes irreversible. One human has experienced near vacuum conditions and survived to describe it. A NASA technician in 1966, testing a spacesuit in a vacuum chamber, suffered accidental decompression to the equivalent of 36,500 meters altitude. He remained conscious for 12 to 15 seconds. His last memory before passing out was the sensation of saliva boiling on his tongue. He regained consciousness 27 seconds later when the chamber was repressurized. No lasting damage. 3 humans have died from vacuum exposure. The Soyuz 11 crew in 1971, when a valve failed during re-entry, exposing them to vacuum at high altitude. By the time ground crews reached the capsule, all 3 cosmonauts were dead, appearing as if they'd simply fallen asleep. Rapid decompression, unconsciousness, death within 2 minutes, while the capsule descended normally on autopilot. This is what interstellar space does to unprotected biology. The vacuum alone would kill you quickly. Add radiation, and survival becomes impossible without extensive shielding. Add the temperature extremes, and even robotic systems struggle with thermal management. Interstellar space is profoundly hostile to anything resembling life as we understand it. Yet Voyager endures, still transmitting after nearly 5 decades in space. Its measurements continue revealing details about this hostile environment. The plasma waves, the particle densities, the magnetic field variations. Each data point maps another small section of the vast unknown that surrounds our solar system, that fills the gaps between stars throughout the galaxy. And this is just the beginning of understanding what's actually out there, what we'd need to survive in it, and what that emptiness truly contains. The emptiness between stars contains something that defies simple classification. We've been calling it vacuum, empty space, the void. Those labels hide what's actually there. Interstellar space isn't empty. It's filled with matter, just not in concentrations we're equipped to comprehend. 1 atom per cubic centimeter on average. Compare that to Earth's atmosphere at sea level, 30 quintillion molecules per cubic centimeter. The ratio is absurd. If you took all the air in a typical bedroom and spread it evenly across the volume of Earth, you'd still have something millions of times denser than typical interstellar space. Yet this isn't truly empty. Those scattered atoms represent about 5% of the Milky Way's total mass. That sparse distribution adds up across galactic scales. Hundreds of billions of solar masses worth of hydrogen and helium drifting between the stars, invisible to casual observation, but gravitationally significant. The composition tells a story of stellar recycling. 70% hydrogen atoms, most of the remainder helium, less than 1% everything else. Those trace elements, carbon, oxygen, iron, silicon, came from stellar cores. When massive stars explode as supernovae, they scatter their enriched interiors across light years. When old stars shed their outer layers as planetary nebulae, those expanding shells seed the interstellar medium with processed material. Every atom heavier than helium was forged inside a star. This matter doesn't exist in a single state. The interstellar medium has phases, distinct regions with wildly different properties. Temperature and density show inverse correlation. Hot regions are diffuse. Cold regions are dense. The physics ensures this through pressure equilibrium. The cold neutral medium sits at 10 to 100 Kelvin. This is where density peaks, where molecular clouds form, where gravity can overcome thermal pressure and collapse matter into new stars. These regions contain 1,000 to 100,000 atoms per cubic centimeter. Still vacuum by terrestrial standards, but dense enough for chemistry. Move to the warm medium, 5,000 to 10,000 Kelvin. This phase exists in both atomic and ionized states, occupying the spaces between clouds. Moderate density, moderate temperature, a transition zone between extremes. Then there's the hot ionized medium. Temperatures from 1 million to 10 million Kelvin, heated by supernova shockwaves. This fills 20 to 60% of the galaxy's volume, but contributes almost nothing to its mass. 0.1 atoms per cubic centimeter or less. The expansion from heating creates enormous bubbles of near-perfect vacuum at temperatures that would vaporize any material substance. These phases coexist, separated by boundaries where physics shifts abruptly. Cross from a molecular cloud into surrounding warm medium and density drops by factors of thousands. Temperature jumps by factors of hundreds. The transitions happen across distances measured in astronomical units, sharp by cosmic standards, but still vast compared to anything in human experience. Voyager's instruments detected these boundaries. The Heliopause, where solar wind meets interstellar medium. Plasma density jumped 40-fold across that transition. The spacecraft went from our sun's bubble of influence into true interstellar space, and the particle environment changed fundamentally. Different composition, different density, different behavior. Those measurements revealed something unexpected. Continuous plasma oscillations, waves propagating through the charged particles, creating a kind of interstellar hum. The frequency of these oscillations depends on electron density. Higher pitch means more particles. Voyager's antennas, 30-foot probes extending behind the spacecraft, detect these vibrations and transmit the data back to Earth. Each wave provides a density measurement, but they're sporadic, appearing roughly once per year in Voyager's data. This makes mapping difficult. We're trying to understand the structure of interstellar space from a single point source moving at 17 kilometers per second, sending back occasional measurements from regions billions of kilometers apart. What we've learned suggests structure we didn't anticipate. The density isn't uniform. It varies, sometimes dramatically, over distances of tens of astronomical units. Local concentrations, rarefied zones, boundaries between different conditions. The interstellar medium has texture. Temperature adds another layer of complexity. That cosmic microwave background radiation sets a baseline of 2.7 Kelvin everywhere. But local conditions determine actual particle temperatures. In the cold molecular clouds, gas temperatures match the background, held down by radiative cooling. In coronal gas heated by stellar violence, particles reach millions of degrees. This creates a conceptual problem. Temperature in vacuum doesn't mean what temperature means on Earth. When we say a region of space has a temperature of 10 million Kelvin, we're describing the kinetic energy of individual particles. Those particles are moving fast enough that if you measured their individual speeds and converted to temperature, you'd get 10 million Kelvin. But there are so few particles that they can't transfer much heat through collisions. An object in that environment wouldn't instantly vaporize despite the extreme temperature. It would slowly gain or lose heat through radiation, through the emission and absorption of photons. The sparse particles hitting it would contribute almost nothing to its thermal balance. This is why Voyager still functions. The spacecraft travels through regions where particle temperatures exceed anything we can create in laboratories. But the particle density is so low that thermal management happens through radiative cooling, not convective or conductive heat transfer. The spacecraft's internal components maintain reasonable temperatures, despite the nominal environment temperature being millions of degrees. Interstellar dust complicates this picture further. Only 1% of the interstellar medium's mass, but those tiny grains have outsized importance. Silicates and carbon compounds, some with ice mantings, others bare. Size scale of 1/10 of a micron, roughly the wavelength of blue light. These grains affect observations profoundly. Light from distant stars passes through thousands of light years of this dust. Each grain scatters and absorbs photons, particularly shorter wavelengths. Blue light gets scattered more efficiently than red light. The result is interstellar extinction, a dimming and reddening of starlight that increases with distance. Astronomers have to correct for this effect when measuring stellar properties. A star's apparent color and brightness don't reflect its true characteristics. The interstellar medium filters that light, removing photons, shifting the spectrum redward. The corrections matter for distance measurements, luminosity estimates, temperature determinations. But dust does more than interfere with observations. It enables chemistry. The grain surfaces provide meeting places for atoms in an environment where gas phase collisions are rare. Hydrogen atoms land on dust grains, stick through van der Waals forces, migrate across the surface, find other hydrogen atoms, bond into molecules, eventually return to gas phase as molecular hydrogen. This process is crucial because molecular hydrogen can't form efficiently through gas phase reactions. The molecule needs to shed energy when it forms, and collisions with third particles are too rare in interstellar space. Dust grains solve this problem by absorbing the excess energy, allowing the molecule to remain bound. Complex chemistry follows. Over 200 molecular species identified in interstellar space so far, the tally growing at roughly 4 discoveries per year. Simple molecules, water, carbon monoxide, ammonia. organic molecules, methanol, formaldehyde, ethanol. Even complex organics, polycyclic aromatic hydrocarbons, molecules with carbon rings that might be precursors to biological chemistry. This chemistry happens despite the cold, despite the low density, despite conditions that seem hostile to chemical reactions. Cosmic rays provide the energy. High-speed protons and heavier nuclei slam into molecules, ionizing them, breaking bonds, creating reactive fragments that recombine into new species. The molecular clouds, those densest regions, become chemical factories. Temperatures near absolute zero, densities of 10,000 particles per cubic centimeter, shielded from ultraviolet radiation by surrounding dust. Molecules can survive and grow more complex in these protected environments. Laboratory experiments try to recreate these conditions. Vacuum chambers cooled to 10 Kelvin, exposed to ultraviolet radiation and particle bombardment, seeded with simple ices. The results show that complex organic molecules form readily under interstellar conditions. Amino acid precursors, nucleotide components, the building blocks of terrestrial biochemistry, arising naturally in space. This raises profound questions about life's origins. Did organic chemistry begin on Earth, or did it begin in space and rain down on the young planet? Meteorites contain organic compounds, demonstrably formed in space before the solar system existed. Comets deliver water and organics during impacts. The boundary between cosmic chemistry and biochemistry might be less sharp than we assumed, but these processes happen slowly. Molecular complexity builds over millions of years in molecular clouds. Stars form from these clouds, carrying their chemical inventory into circumstellar disks. Planets condense from those disks, inheriting molecules synthesized during the cloud's lifetime. The chemistry in your body might have started in interstellar space billions of years before Earth existed. Cosmic rays thread through all of this, high-energy particles racing through the galaxy at near light speed. 89% protons, 10% helium nuclei, 1% heavier elements up to uranium. Stripped of electrons, accelerated by supernova shockwaves and other violent events, they carry energies from giga-electron volts to 100 million tera-electron volts. The highest energy cosmic rays exceed anything we can produce in particle accelerators. The Large Hadron Collider peaks at 14 tera-electron volts. Individual cosmic ray particles reach 100 million times that energy. Nobody knows how nature accelerates particles to such extremes. These particles interact with everything they encounter. Collisions with atomic nuclei in molecular clouds produce gamma rays. Collisions with photons in the cosmic microwave background boost those photons to X-ray and gamma-ray energies through inverse Compton scattering. The interstellar medium glows faintly across the electromagnetic spectrum from these interactions. For space travel, cosmic rays represent a radiation hazard without simple solutions. Their energy is too high for conventional shielding. A cosmic ray particle can penetrate meters of solid material, leaving a trail of ionization damage. Thick shielding helps, but adds mass. Active magnetic shielding might deflect charged particles, but requires enormous power. The radiation dose in interstellar space, far from any star's protective influence, would be lethal over timeframes measured in months, without shielding measured in meters of water or equivalent material. Even with shielding, the secondary radiation produced when cosmic rays interact with the shield material creates additional exposure. Voyager experiences this radiation constantly. The spacecraft's electronics suffer gradual degradation from particle impacts. Memory upsets occur when cosmic rays flip bits in computer memory. Component failures accumulate. The mission team works around these issues, reprogramming systems to avoid damaged components, adjusting operations to account for reduced capability. Each particle hit leaves permanent damage in the spacecraft's materials. The cumulative effect after decades of exposure shows in component failures and data anomalies. Yet Voyager endures, still transmitting, still gathering data from an environment that would kill unprotected humans in minutes. Human bodies weren't designed for interstellar space. The vacuum, the radiation, the temperature extremes, each factor independently lethal. Combined, they create an environment of almost perfect hostility to biological life as Earth produces it. Even microbial extremophiles adapted to Earth's harshest environments would struggle to survive unprotected exposure to interstellar conditions. Yet life might exist out there, protected by different strategies, adapted to different conditions. Hypothetical organisms in the atmospheres of rogue planets, worlds ejected from their star systems and wandering through interstellar space. Life in subsurface oceans of frozen moons, heated by tidal forces or radioactive decay. Chemistry we don't recognize as biology, using different solvents, different energy sources, different reproductive strategies. The search for such life requires understanding what interstellar space actually contains, how its chemistry works, what energy sources exist. Voyager's measurements provide our first ground truth, direct sampling of the interstellar medium's composition and behavior. Each data transmission adds detail to our map of what's out there between the stars. The data reveals structure nobody expected, temperature variations across regions. Voyager samples suggest the interstellar medium isn't uniform. Pockets of warmer plasma alternate with cooler zones. Density fluctuates. The spacecraft passes through regions where electron density climbs, then drops, then rises again. These variations occur on scales of astronomical units, structures that would take Voyager months or years to traverse at its current speed of 38,000 miles per hour. What creates these structures? Supernova remnants, for one. When massive stars explode, they blast shells of material outward at thousands of kilometers per second. These expanding bubbles sweep up surrounding gas, compressing it, heating it, creating cavities of hot, thin plasma surrounded by denser, cooler shells. The shock waves from supernova explosions that occurred thousands or millions of years ago still ripple through local interstellar space, shaping the medium Voyager samples today. Stellar winds contribute too. Every star emits a wind of charged particles, weaker than the sun's in most cases, stronger in others. Hot, luminous stars produce intense winds that carve bubbles in the interstellar medium. Wolf-Rayet stars, massive stars in late evolutionary stages, blow winds so powerful they can clear regions hundreds of light years across. These winds collide with surrounding material, creating turbulence, mixing elements, heating gas to millions of degrees. The local interstellar medium surrounding our solar system sits inside one such bubble. The local bubble, astronomers call it. A cavity roughly 300 light-years across, carved by supernova explosions that occurred several million years ago. The solar system currently lies near the edge of this bubble, approaching the boundary where hot, thin gas transitions to cooler, denser material beyond. Voyager's trajectory carries it through the outer regions of this structure. The spacecraft's instruments measure the density, temperature, and magnetic field orientation of plasma that fills this cavity. Each measurement adds detail to our understanding of how stellar explosions shape galactic structure, how energy and matter circulate through the galaxy, how the conditions Earth experiences connect to processes occurring on vast scales. The magnetic field threading through interstellar space deserves particular attention. Voyager's magnetometer detects field strengths of a few microgauss, millions of times weaker than Earth's magnetic field at the surface. Yet this weak field plays crucial roles. It guides the motion of charged particles, cosmic rays included. It stores energy that can be released in magnetic reconnection events. It couples to turbulent motions in the plasma, creating waves that propagate across interstellar distances. Magnetic fields in the interstellar medium align roughly with the galactic plane, but show local variations. Supernova shockwaves compress fields. Turbulent motions twist them. The overall structure resembles a tangled mess when examined closely, yet statistical analyses reveal patterns on larger scales. The field strength scales with density in predictable ways. The orientation correlates with large-scale flows of gas around the galaxy. This field affects everything moving through interstellar space. Cosmic rays spiral along magnetic field lines, their trajectories bent by the field's influence. Lower energy cosmic rays remain confined near their sources for longer periods, while higher energy particles eventually escape the galaxy entirely. The magnetic field creates a kind of cosmic ray ecosystem, trapping some particles, guiding others, allowing the highest energy examples to escape into intergalactic space. Voyager measures this field directly. The spacecraft's magnetometer records three-dimensional field vectors every few seconds, building a dataset that spans years of travel through interstellar space. Analysis reveals variations on multiple timescales. Rapid fluctuations suggest plasma waves passing the spacecraft. Slower changes indicate regions with different field properties. The longest-term trends show the spacecraft moving through large-scale structures in the local interstellar medium. Temperature in this environment demands careful interpretation. When physicists say interstellar plasma has a temperature of 10,000 Kelvin or 1,000,000 Kelvin, they're describing the average kinetic energy of particles. Individual protons or electrons move at speeds corresponding to these temperatures, but the density is so low that an object placed in this plasma wouldn't heat up to that temperature through conduction or convection. Heat transfer requires particle collisions. With only one atom per cubic centimeter, collisions happen too infrequently to transfer significant energy. Instead, objects in interstellar space lose or gain heat primarily through radiation. A spacecraft absorbs cosmic microwave background radiation at 2.7 Kelvin. It absorbs starlight, which adds heat depending on distance from stars. It radiates heat as infrared based on its own temperature. The equilibrium temperature depends on the balance between absorbed and emitted radiation, not the kinetic temperature of surrounding plasma. Voyager's thermal control systems account for this. The spacecraft carries heaters to keep sensitive components warm enough to function. Power from the radioisotope thermoelectric generators provides heat in addition to electricity. As power output declines with the radioactive decay of plutonium-238, thermal management becomes increasingly challenging. Mission controllers adjust heater usage, powering down non-essential systems to conserve power for instruments and heaters protecting critical components. The spacecraft's operating temperature hovers around 5 degrees Celsius for most systems. Some components run warmer, others cooler. The balance shifts as power availability decreases. By the 2030s, power output will drop below levels needed to maintain current operations. The mission team will face difficult choices about which instruments to keep running, which systems to shut down, how long to extend the mission before communication becomes impossible. Even after Voyager stops transmitting, the spacecraft will continue its journey. The inert machine will coast through interstellar space for millions of years, gradually cooling to match the cosmic microwave background temperature. Its trajectory will carry it past other stars eventually. In about 40,000 years, Voyager 1 will pass within 1.6 light-years of the star Gliese 445. Closer approaches will occur over hundreds of thousands and millions of years as the spacecraft wanders the galaxy. The golden record attached to each Voyager carries information about Earth and humanity. Images, sounds, music, greetings in multiple languages. The chance of another civilization finding either spacecraft is astronomically small. Space is vast. The probability that Voyager's trajectory intersects another technological civilization approaches zero. Yet the gesture matters. We sent messages in bottles into the cosmic ocean, acknowledging the possibility, however remote, that we're not alone. The chemistry occurring in interstellar space surprises researchers. Despite the extreme emptiness, chemical reactions proceed. Molecules form, grow complex, eventually create the building blocks of life. Radio astronomy reveals over 200 molecular species in interstellar space, from simple diatomic molecules like carbon monoxide to complex organic compounds. The process begins with ionization. Cosmic rays strike hydrogen atoms, knocking electrons free. The resulting protons can combine with neutral hydrogen to form molecular hydrogen ions. These ions react with other atoms and molecules, building complexity step by step. Reactions that would be impossible in terrestrial environments proceed because the extreme cold and low density create conditions where even unlikely reactions eventually occur, given enough time. Molecular clouds, the densest regions of interstellar space, host the most active chemistry. Densities of 10,000 to 100,000 atoms per cubic centimeter allow more frequent collisions. Temperatures of 10 to 50 Kelvin slow molecular motion, increasing reaction times. Dust grains provide surfaces where molecules can meet and react. Ice mantles coating dust grains enable chemistry impossible in the gas phase. The molecules formed include water, ammonia, methanol, formaldehyde. More complex species like amino acids likely form under certain conditions, though detecting them remains challenging. Polycyclic aromatic hydrocarbons, rings of carbon atoms with attached hydrogen, appear widespread. These molecules absorb ultraviolet light and re-emit it as infrared, making them detectable through spectroscopy. Some molecular clouds contain alcohol. Ethanol, the alcohol in beverages, exists in clouds light years across. One cloud near the constellation Aquila contains enough ethanol to fill 1 trillion pints. Not that anyone could collect it. The density averages a few molecules per cubic centimeter. You'd have to compress a volume larger than Earth to collect a single glass. These molecules eventually incorporate into new stars and planets. When molecular clouds collapse under their own gravity, the chemistry already present becomes the starting material for planetary systems. Earth's water likely includes molecules that formed in interstellar space before the solar system existed. The carbon in your body, the nitrogen, the oxygen, all cycled through interstellar space as simple molecules before ending up in you. Dust grains themselves deserve attention. These particles, typically 1/10 of a micron across, compose only 1% of the interstellar medium's mass, but profoundly affect observations. They scatter and absorb starlight, particularly blue wavelengths, making distant stars appear redder than they actually are. They dim starlight, requiring corrections when calculating stellar distances and luminosities. The composition includes silicates similar to beach sand, carbon in the form of graphite or more complex structures, and ices that freeze onto grain surfaces in cold regions. Laboratory analysis of meteorites reveals pre-solar grains, dust that formed around other stars before incorporating into the solar nebula. These grains preserve records of stellar nucleosynthesis, supernova explosions, and interstellar processing that occurred billions of years ago. Dust formation occurs primarily around dying stars. Red giants and supergiants shed material in stellar winds. The gas cools as it moves away from the star. At temperatures below 1500 Kelvin, atoms begin condensing into solid grains. Different stars produce different dust compositions depending on their chemistry. Carbon stars make carbon dust. Oxygen-rich stars produce silicates. Supernova explosions also create dust. The expanding ejecta cools rapidly. Elements synthesized in the explosion condense into grains within the expanding shell. Observations of young supernova remnants reveal substantial dust masses forming in these environments, contributing to the interstellar dust budget. Once formed, dust grains survive for hundreds of millions of years in interstellar space. Supernova shockwaves can destroy them through sputtering, knocking atoms off grain surfaces. Collisions between grains moving at different speeds can shatter them. But the interstellar medium is so empty that destructive events occur infrequently. Most grains persist until they incorporate into new stars. These grains enable planet formation. In the disks surrounding young stars, dust grains stick together through electrostatic forces and gentle collisions. Centimeter-sized pebbles grow into meter-sized rocks, eventually forming kilometer-sized planetesimals. Without dust, rocky planets like Earth wouldn't exist. The solid material needed to build worlds began as microscopic grains floating in interstellar space. Voyager carries no instruments designed to detect dust directly. The spacecraft's cosmic ray detector occasionally registers impacts from dust grains, but these events are rare and difficult to distinguish from other particle hits. Our knowledge of interstellar dust comes primarily from astronomical observations and laboratory analysis of meteorites and returned comet samples. The spacecraft does measure something dust affects: the interstellar radiation field. Starlight scattered by dust grains creates a diffuse glow throughout the galaxy. Voyager's ultraviolet spectrometer can measure this radiation, providing indirect information about dust distribution. The measurements remain challenging. The signal is faint. Separating interstellar contributions from zodiacal light, sunlight scattered by dust in our solar system, requires careful analysis. Plasma waves detected by Voyager provide another window into interstellar conditions. These waves result from instabilities in the plasma, disturbances that propagate through the medium like sound waves through air. The frequencies correspond to electron densities. Higher-pitched oscillations indicate denser plasma. Lower frequencies suggest thinner regions. The discovery that these waves occur continuously, not just during sporadic events, surprised researchers. Earlier predictions suggested plasma oscillations would occur mainly when disturbances from the Sun's activity reached interstellar space. Instead, Voyager finds the interstellar medium naturally generates these waves through its own dynamics. What drives this activity? Cosmic rays likely play a role. Their passage through plasma creates instabilities that generate waves. Turbulent motions in the interstellar medium might contribute. Magnetic reconnection events, where twisted magnetic field lines snap and reconfigure, release energy that excites plasma oscillations. The exact mechanisms remain under investigation. Each wave carries information. Its frequency reveals local electron density. Its amplitude suggests the strength of the disturbance that generated it. Its evolution over time shows how plasma properties change as Voyager moves through different regions. The dataset accumulates slowly, one measurement at a time, building a picture of interstellar space that grows more detailed with each passing year. Human exploration of this environment remains science fiction. The distances are too vast, the hazards too severe, the energy requirements too enormous. But robots can go. Spacecraft like Voyager demonstrate that machines can survive the journey, can gather data, can transmit discoveries across billions of miles. Future missions might carry more sophisticated instruments, nuclear batteries lasting centuries, communication systems maintaining contact across interstellar distances. Engineers have proposed designs. Project Longshot, a conceptual spacecraft using nuclear pulse propulsion, could theoretically reach Alpha Centauri in a century. Breakthrough Starshot suggests using laser-pushed light sails to achieve relativistic speeds, reaching nearby stars within decades. These remain proposals. The technical challenges are immense, the costs astronomical. But the concepts prove that interstellar travel isn't impossible, merely extraordinarily difficult. Voyager shows what's possible with 1970s technology and determination. The spacecraft continues functioning decades beyond its design lifetime, still gathering data in an environment its builders could only imagine. Each transmission proves that the boundary between possible and impossible isn't fixed. It shifts when we push against it. The information arrives in patterns. Data streams compress into files. Files transform into graphs. Graphs reveal truths about an environment no human will visit for centuries, if ever. Voyager's measurements show the interstellar medium isn't uniform. Density fluctuates, temperature varies, magnetic fields twist and coil through space. The spacecraft travels through a medium that changes around it, though the changes occur over scales of billions of miles and timescales of years. The magnetic field deserves special attention. Inside the heliosphere, the Sun's magnetic field dominates. Its structure reflects the solar wind's outward push, creating a spiral pattern as the Sun rotates. Beyond the Heliopause, galactic magnetic fields take over. These fields aren't static. They permeate the galaxy, threading through space between stars. Their strength measures in microgauss, millions of times weaker than Earth's magnetic field. Yet they exert profound influence on cosmic ray propagation, charged particle motion, and the structure of the interstellar medium itself. Voyager carries a magnetometer, The instrument measures field strength and direction. Its data reveals how magnetic field lines orient in interstellar space, how they connect to the heliosphere's edge, how they channel particles and shape plasma flows. One discovery startled researchers. The magnetic field direction in interstellar space aligns differently than models predicted. The field runs roughly parallel to the Heliopause boundary, not perpendicular as some theories suggested. This orientation affects how the heliosphere interacts with its environment, how cosmic rays penetrate our solar system, how the boundary between solar and galactic influences evolves. The field's structure connects to larger galactic processes. Supernova explosions inject energy into interstellar space, heating gas to millions of degrees and creating expanding bubbles that push against surrounding material. These bubbles stretch and amplify magnetic fields. The Sun might currently reside near the edge of one such bubble, a region called the local bubble, created by supernovae explosions millions of years ago. Understanding this environment requires combining Voyager's measurements with observations from other sources. Radio telescopes detect emissions from ionized gas. X-ray observatories map hot plasma. Optical telescopes trace dust lanes. Ultraviolet instruments measure absorption by interstellar atoms. Each wavelength reveals different aspects of the same environment. Radio waves show where magnetic fields accelerate electrons. X-rays highlight regions heated by shock waves. Visible light scatters off dust grains. Ultraviolet absorption indicates atomic gas density. Voyager provides ground truth. Its in-situ measurements calibrate remote observations. When telescopes detect certain emission lines, Voyager's instruments confirm the plasma density producing those lines. When models predict magnetic field strengths, Voyager's magnetometer tests those predictions. The spacecraft serves as an anchor point for interpreting signals from regions we cannot directly measure. But Voyager samples only one path through interstellar space, one trajectory through a medium that varies in 3 dimensions. Imagine trying to understand an ocean by dragging a single thermometer through it. You'd measure temperature along your path, but you'd miss currents, upwellings, and thermal layers elsewhere. Similarly, Voyager reveals conditions along its route, but interstellar space contains structure the spacecraft doesn't encounter. Dense molecular clouds where stars form, hot bubbles carved by stellar winds, shock fronts from ancient supernovae. Each region has different density, temperature, composition, and magnetic properties. The spacecraft won't sample these variations. Its trajectory carries it through one narrow slice of the galaxy's disk, then gradually out into the halo. The environments it encounters over coming decades will change, but slowly, as it crosses boundaries between different regions of the interstellar medium. Other spacecraft might eventually follow. Voyager 2 travels a different path, measuring conditions in another direction. New Horizons, launched in 2006, will reach the Heliopause sometime in the 2040s, providing a third measurement point. Proposals exist for dedicated interstellar probes equipped with modern instruments designed specifically for studying the local interstellar medium. These missions remain concepts. Funding hasn't materialized, technical challenges abound, but the possibility exists that future spacecraft will map interstellar space more thoroughly, revealing its 3-dimensional structure, tracing magnetic field lines across vast distances, measuring how conditions vary with direction and distance from the Sun. What would we find? Current models suggest the local interstellar medium has structure on multiple scales. The Sun moves through a small cloud of slightly denser material called the local interstellar cloud. This cloud exists within the larger local bubble, that cavity carved by ancient supernovae. Beyond the bubble lies denser material, including molecular clouds and star-forming regions. The Sun's motion carries it through these structures. Over millions of years, the solar system traverses different environments. Sometimes it passes through dense clouds that compress the heliosphere. Other times, it enters regions so tenuous the heliosphere expands to enormous size. These variations have consequences. When the heliosphere shrinks, more cosmic rays penetrate the inner solar system. Earth's atmosphere receives higher radiation doses. Climate might be affected through cosmic ray interactions with clouds. The geological record possibly preserves evidence of these encounters in isotope ratios produced by cosmic ray bombardment. Voyager can't measure these long-term variations directly. The spacecraft's mission spans decades, not millions of years. But its measurements provide a baseline. They show conditions in the interstellar medium during this epoch. Future missions might detect changes as the Sun moves into different regions. The radiation environment particularly matters for any future interstellar exploration. Cosmic rays in interstellar space pose severe hazards. Voyager's instruments measure their intensity, energy spectrum, and composition. The data reveals radiation levels that would quickly incapacitate unshielded humans. Consider the numbers. Cosmic ray flux in interstellar space delivers roughly 70 rem per year to an unshielded object. For comparison, NASA's current annual limit for astronauts is 50 rem over their entire career. A journey to even the nearest star would accumulate doses far exceeding safe limits. Shielding helps, but creates new problems. Traditional materials like aluminum or lead stop cosmic rays, but the collisions produce secondary radiation that's sometimes more dangerous than the primaries. When high-energy cosmic rays strike atomic nuclei in shielding material, they fragment both the cosmic ray and the target nucleus, creating showers of particles that penetrate deeper into the spacecraft. Better shielding requires different approaches. Hydrogen-rich materials like water or plastics produce fewer secondary particles. Magnetic fields could deflect charged particles. Active shielding systems might detect incoming cosmic rays and generate localized fields to divert them. None of these solutions are proven at the scales needed for interstellar travel. The human body itself becomes radioactive. Cosmic rays striking atoms in tissue produce unstable isotopes. Carbon-14, formed when cosmic rays hit nitrogen, accumulates in bones and organs. Other radioactive elements appear. The body becomes a low-level radiation source, slowly damaging its own cells even after the external radiation stops. Repair mechanisms handle some damage. DNA repairs itself. Cells replace damaged components. But cosmic ray hits cause complex injuries that overwhelm these systems. A single high-energy particle traversing a cell nucleus can shatter chromosomes in multiple places. The repair machinery might reconnect the pieces incorrectly, creating mutations that lead to cancer decades later. These aren't theoretical concerns. Studies of astronauts show increased cancer rates correlating with radiation exposure. Experiments with cells and animals demonstrate the biological effects. Mathematical models predict outcomes for long-duration missions. All point to the same conclusion. Interstellar space is intensely hostile to biological life, yet life might exist there. Not complex organisms, but microorganisms. Bacteria can survive extreme radiation doses. Tardigrades tolerate vacuum. Bacterial spores remain viable for years in space conditions. Could such organisms cross interstellar distances? Panspermia, the hypothesis that life spreads between stars, requires mechanisms to transport viable organisms across the void. Rocks ejected from planetary surfaces by asteroid impacts might serve as vehicles. Some Mars meteorites reached Earth with interiors that never heated above temperatures harmful to bacteria. Similar rocks might travel between star systems. The journey would take millions of years. Radiation would bombard the rock's surface, but interior regions might remain shielded. Cosmic ray exposure would still occur, but at reduced intensity. Organisms in the deepest crevices might survive if they could endure prolonged dormancy. Laboratory experiments test these limits. Bacteria exposed to simulated interstellar conditions show survival rates that decline but don't reach zero. Some fraction remains viable even after years of exposure. The numbers are small, but given enough rocks launched into space over billions of years, even tiny survival probabilities might allow life to spread. Voyager carries no life detection instruments. The spacecraft wasn't designed to search for organisms, but its measurements characterize the environment where panspermia would occur. The radiation levels, temperature extremes, and vacuum conditions define the challenge any organism must overcome to traverse interstellar space. The data suggests the barriers are high, but perhaps not insurmountable. The challenge shifts to understanding how often viable organisms get ejected from planets, what fractions survive the journey, and whether they could establish themselves upon arriving at new worlds. These questions extend beyond academic curiosity. If panspermia occurs, it affects how we interpret discoveries of life elsewhere. Finding bacteria on Mars might mean they originated on Earth. Detecting biosignatures on exoplanets might indicate life spread from a common source. Understanding interstellar transfer mechanisms becomes crucial for interpreting observations. Voyager's measurements contribute one piece to this puzzle. The spacecraft maps the environment through which panspermia must occur. It quantifies the hazards. It reveals the medium's structure. This information constrains models and guides future research. The spacecraft also demonstrates survival itself. Voyager functions in an environment that would quickly destroy biological tissue. Its electronics endure radiation that would be lethal to humans. Its structure withstands temperature extremes and micrometeorite impacts. The machine persists where flesh cannot. This endurance offers lessons for future missions. The engineering choices made in the 1970s, the materials selected, the component redundancy built in, all contribute to the spacecraft's longevity. Modern missions could improve on these designs using advanced materials and radiation-hardened electronics developed in recent decades. But Voyager's real achievement isn't technical, it's conceptual. The spacecraft proved that machines can enter interstellar space and return data. It demonstrated that the boundary between solar and galactic environments can be crossed, measured, and understood. It showed that what seems impossible becomes merely difficult when approached systematically. The heliopause isn't a wall. Interstellar space isn't instantly lethal to spacecraft. The void between stars contains structure, variation, and phenomena worth studying. These revelations emerged not from theory, but from direct measurement, from actually going there and looking. Future missions will build on this foundation. They'll carry better instruments, travel faster, last longer. But they'll follow the path Voyager blazed, venturing into an environment that was purely theoretical before 2012. The spacecraft's trajectory defines its ultimate fate. Voyager moves at 17 kilometers per second relative to the Sun. This velocity won't change significantly. No gravitational field strong enough to alter the path exist in interstellar space. The spacecraft will coast on its current heading for thousands of years before approaching another star. In 40,000 years, Voyager 1 will pass within 1.6 light-years of Gliese 445. That's the closest stellar approach predicted for either spacecraft. The encounter won't be dramatic. At that distance, the star's gravity is negligible. Voyager will simply drift past, continuing its journey into deeper space. The spacecraft carries more than scientific instruments. Mounted on each Voyager is a golden record. These phonograph discs contain sounds and images selected to represent Earth's diversity. Greetings in 55 languages, music from different cultures and eras, natural sounds like thunder, wind, and animal calls. The records include diagrams showing Earth's location and instructions for playback. The golden records assume someone might find them. The probability is vanishingly small. Space is vast. Even within the galaxy, stellar distances make chance encounters unlikely. The records might drift for billions of years without passing near any planetary system. They might never be discovered at all. But the gesture matters independently of outcome. Creating the records forced consideration of how to communicate across species, across cultures, across time itself. What do you include when speaking to unknown minds? How do you convey meaning when you can't assume shared language or sensory experience? The selection process revealed assumptions about universality. Mathematics was deemed universal. Physical constants were thought comprehensible to any technological civilization. Music and art were included with less certainty about translation. The records will outlast their creators. Gold doesn't corrode in vacuum. The discs should remain playable for billions of years. Longer than Earth's continents will maintain their current shapes. Longer than the Sun will remain on the main sequence. The records become time capsules preserving evidence of a civilization that might not exist when they're found. This permanence carries philosophical weight. The spacecraft and records represent humanity's first truly permanent artifacts. Everything else we've created will eventually decay. Cities will erode. Digital storage will fail. Even radioactive waste will eventually stabilize. But the golden records, traveling through near-perfect vacuum, will persist essentially unchanged. Voyager's power supply creates a different timeline. The spacecraft's plutonium generators decay at a fixed rate. Power output drops continuously. Engineers manage this decline by shutting down non-essential systems. The tape recorder stopped operating in 2007. Several science instruments have been turned off to conserve energy. By 2025, power levels will require additional shutdowns. The remaining instruments will be prioritized based on science value. Some will continue operating while others go dormant. This triage will continue as power declines further. Sometime around 2036, power will drop below the threshold needed to operate any instruments. Voyager will go silent. The spacecraft will continue moving through space, but it will stop transmitting. Its observations of interstellar space will end. The silence won't mean death. The spacecraft will still exist, still travel, still carry the golden record. It just won't communicate. This distinction matters for understanding what exploration means. Voyager won't stop exploring space. It will stop telling us what it finds. Future civilizations might recover the spacecraft. Technology for intercepting and retrieving objects in interstellar space doesn't exist now, but it might eventually. A sufficiently advanced civilization could track Voyager's trajectory, match velocities, and bring it aboard. The data stored in its memory could be downloaded. The instruments could be examined. The golden record could be played. This scenario requires assumptions about technological development and motivation. A civilization capable of interstellar travel would need reasons to bother with a primitive probe. The golden record might provide that reason, or simple curiosity about other civilizations might suffice. The spacecraft's design contains information beyond the golden record. The materials used, the construction techniques, the instrument specifications, all reveal technological capabilities. Examining Voyager would show what Earth's civilization could accomplish in the 1970s. The spacecraft becomes an archaeological artifact, a snapshot of technological development frozen at launch. Voyager's journey changes how we think about exploration. Previous expeditions sent people or retrieved samples. They depended on return journeys. Voyager represents pure outward motion with no return. The spacecraft will never come back. The data it sends will be its only contribution. This one-way nature affects mission design. Engineers don't need to plan for return trajectories or landing sequences. They can optimize purely for distance and longevity. The spacecraft can be lighter, simpler, more focused on its outbound objectives. The approach also affects psychology. Voyager's journey has no homecoming. There's no triumphant return to celebrate. The mission's end will be silence, not arrival. This changes the emotional relationship to the endeavor, but it also creates different kinds of achievement. Voyager's distance records will likely stand for decades. No other human-made object has traveled farther. None has entered interstellar space before. These firsts matter independently of return. The spacecraft's measurements reveal environmental conditions that constrain future missions. Any probe sent to another star must survive the radiation levels Voyager measures. It must withstand the dust impacts the spacecraft records. It must function in the temperature extremes the instruments detect. Voyager provides a baseline for interstellar engineering. Designers of future missions can reference its data when selecting materials and components. They can anticipate hazards based on Voyager's observations. The spacecraft serves as pathfinder for journeys not yet undertaken. The plasma waves Voyager detected demonstrate this value. Before crossing the Heliopause, scientists could only theorize about conditions in interstellar space. Models predicted certain properties, but uncertainty remained. Voyager's measurements turned speculation into data. The electron density surprised researchers. Theoretical predictions suggested lower values. The observed density, 40 times higher than expected in some regions, forced model revision. This matters for understanding how the interstellar medium affects spacecraft systems. Higher electron density means more interactions with charged particles. Spacecraft surfaces accumulate electrical charge more rapidly. This charge can affect sensitive instruments or discharge suddenly, potentially damaging electronics. Designers of future missions must account for these effects. The temperature structure also revealed unexpected complexity. Interstellar space isn't uniformly cold. Regions of hot ionized gas coexist with cold neutral material. The boundaries between these phases create transition zones where temperature and density change rapidly. Voyager's measurements map this structure along one trajectory. The spacecraft samples a line through interstellar space. Extrapolating from this line to three-dimensional structure requires assumptions. The medium might be uniform across large regions, or it might vary significantly in directions Voyager doesn't travel. Additional probes traveling in different directions could resolve this uncertainty. Multiple trajectories would provide sampling points across a volume rather than along a line. This would reveal whether Voyager's measurements are typical or exceptional. But launching additional interstellar probes presents challenges. Reaching Voyager's distance requires decades. Gravity assists from outer planets provide the necessary velocity, but planetary alignments suitable for such assists occur infrequently. The next opportunity comparable to Voyager's trajectory won't occur for over a century. New Horizons, launched in 2006, might eventually reach interstellar space. The spacecraft is currently beyond Pluto, traveling outward at 14 kilometers per second. Its trajectory will carry it past the Heliopause, though this won't happen until the 2040s or 2050s. When New Horizons crosses that boundary, it will provide a second data point. Scientists can compare its measurements to Voyager's readings. Differences would indicate spatial variation in the interstellar medium. Similarities would suggest larger-scale uniformity. The spacecraft carries different instruments than Voyager. Some capabilities overlap, but New Horizons includes updated detectors developed decades after Voyager's design. This allows observations Voyager couldn't make, while also providing redundancy for key measurements. Planning missions on these timescales requires institutional stability. The scientists who designed Voyager in the 1970s mostly didn't live to see it enter interstellar space in 2012. The researchers analyzing New Horizons data in the 2040s haven't started their careers yet. This generational handoff characterizes deep space exploration. Individual careers span decades. Mission timelines span generations. Maintaining institutional knowledge becomes crucial. Documentation must preserve not just technical specifications, but also the reasoning behind design choices. Voyager demonstrates this challenge. Original engineers have retired or died. Current mission operators weren't born when the spacecraft launched. They work with documentation created before they existed, maintaining systems designed by people they never met. The spacecraft itself provides continuity. Its signals arrive daily. Its instruments still function. The hardware persists while the people change. This persistence grounds the mission despite personnel turnover. Power management illustrates the transition. Early mission operators could run all systems simultaneously. Current teams must carefully budget remaining power. Future operators will face even tighter constraints as output continues declining. Each shutdown decision becomes permanent. Once an instrument is turned off to save power, turning it back on wastes energy. The system must stay off. This creates an irreversible sequence of capability loss. Prioritizing which instruments to keep operating involves scientific judgment. Which measurements provide the most value? Which observations are unique? Which data can't be obtained any other way? The magnetometer remains high priority because it measures fields that vary with position. Later missions traveling different paths won't replicate Voyager's measurements. The cosmic ray detector provides similar unique data about particle distributions. The plasma wave instrument justified its priority through unexpected discoveries. The interstellar plasma oscillations it detected weren't anticipated. Keeping it active revealed phenomena that would have been missed if it had been shut down earlier. This unpredictability argues for maintaining diverse capabilities as long as possible. You can't know in advance which instruments will make surprising discoveries. Shutting down systems prematurely might eliminate the very detector that would have found something remarkable. But power limitations force choices. Not everything can continue operating. Some capabilities must be sacrificed to preserve others. The decisions shape what humanity learns about interstellar space. Voyager's declining power also creates urgency around data analysis. The spacecraft will go silent eventually. Once transmission stops, no new measurements will arrive. Scientists must extract maximum value from the data while it's still flowing. This drives research into subtle effects that might be present in existing datasets. Are there patterns in the plasma wave data that haven't been noticed? Do correlations exist between different instrument readings that reveal underlying physics? Machine learning algorithms increasingly assist this analysis. The datasets are large. Decades of measurements create millions of data points. Automated pattern recognition can identify features human analysts might miss. But interpretation still requires human judgment. Algorithms flag potential signals. Scientists must determine whether those signals represent real phenomena or artifacts of instrumental noise. This filtering process demands understanding of both the physics and the instruments. Voyager's legacy extends beyond its direct measurements. The spacecraft inspired generations of scientists and engineers. Many researchers currently working in planetary science or space physics cite Voyager as early motivation. The images it returned and the discoveries it made shaped career choices. This influence will continue as Voyager's journey extends further into interstellar space. The spacecraft becomes more than a machine. It represents human capability to reach beyond our immediate environment, to explore regions no human will visit, to expand knowledge through persistent observation. The golden record adds symbolic dimension to this practical achievement. Whether or not anyone ever finds it, the record represents an attempt to communicate across cosmic distances and timescales. It's a message to the universe, an assertion that we exist, that we create, that we wonder about others. Voyager will continue its journey long after everyone currently alive is gone. The spacecraft will outlast nations, languages, possibly our entire civilization. It becomes a monument more permanent than anything constructed on Earth's surface, and it moves ever outward, carrying its message into the darkness between stars. That journey continues through what might seem like emptiness, but contains structures invisible to human senses. Interstellar space isn't truly empty. It contains matter, just distributed so thinly that it represents one of the best vacuums in the known universe. Consider the scale of this emptiness. Air at sea level contains roughly 30 quintillion molecules per cubic centimeter. The average interstellar medium contains about 1 atom per cubic centimeter. That's a density difference so vast, it defies intuitive comprehension. Earth's atmosphere is 30 million trillion times denser than the space between stars. Even calling it a vacuum understates the reality. The best laboratory vacuums achieved on Earth contain around 10,000 atoms per cubic centimeter. Interstellar space is 10,000 times emptier than anything we can create artificially. It represents a degree of emptiness that exists nowhere on Earth's surface or in our experience. But this near-perfect vacuum contains structure. The interstellar medium exists in distinct phases with radically different properties. Cold neutral regions hover between 10 and 100 Kelvin, serving as birthplaces for new stars. Warm medium zones reach 5,000 to 10,000 Kelvin, existing in both atomic and ionized states. Hot ionized regions achieve temperatures of 1 million to 10 million Kelvin, heated by supernova shockwaves. These phases demonstrate an inverse relationship between temperature and density. Hot regions expand until their pressure matches surrounding cold gas, creating vast volumes of extremely dilute but intensely hot plasma. The hottest interstellar gas can exceed 8,000 Kelvin, yet an object placed within it would barely feel this heat. Temperature in vacuum means something different than temperature on Earth. With so few particles present, heat transfer through conduction or convection becomes negligible. An object in interstellar space primarily exchanges heat through radiation. Those high-velocity particles might have tremendous kinetic energy individually, but there aren't enough of them to transfer significant thermal energy to larger objects. The composition of this tenuous matter reflects the universe's chemical evolution. Hydrogen comprises roughly 90% of all atoms. Helium accounts for most of the remaining 10%, and everything heavier than helium makes up less than 1%. These heavier elements originated inside stars, ejected into space through stellar winds, planetary nebulae, and supernova explosions. Voyager's instruments measure this composition directly. The plasma wave detector responds to electron oscillations, whose frequency depends on particle density. The cosmic ray detector registers high-energy nuclei from distant stellar explosions. The magnetometer tracks magnetic field variations that reveal how charged particles distribute themselves through space. These measurements reveal densities that surprised researchers. When Voyager 1 crossed into interstellar space, its instruments detected plasma 40 times denser than predicted, based on models of the outer heliosphere. This discovery forced revisions to theories about how the Sun's influence transitions into the broader interstellar environment. That transition occurs at the Heliopause, where solar wind pressure balances against interstellar medium pressure. The heliosphere acts as a protective bubble, shielding our solar system from the full intensity of galactic cosmic rays. This protection fluctuates over time. When the Sun passes through denser interstellar clouds, the heliosphere shrinks. When moving through more dilute regions, it expands. Currently, the heliosphere extends roughly 120 astronomical units before the heliopause marks its boundary. But this size isn't constant. Several 100,000 years from now, the solar system will likely encounter denser interstellar clouds that could compress the heliosphere substantially. Several 100,000 years ago, it probably extended even farther than today. Cosmic rays represent one of interstellar space's most dangerous aspects. These high-energy particles consist primarily of protons, with smaller fractions of helium nuclei and heavier elements. They've been accelerated to nearly light speed, stripping away their electrons and leaving only bare atomic nuclei. The energy distribution is staggering. Primary cosmic rays range from around 1 giga-electron volt to 100 million tera-electron volts. The highest energies exceed anything achievable in the Large Hadron Collider. These particles carry energies comparable to baseballs thrown at highway speeds, concentrated in single atomic nuclei. When cosmic rays collide with interstellar matter, they generate secondary radiation. Impacts with atomic nuclei produce gamma rays. Electrons scatter photons from the cosmic microwave background and starlight, boosting them to X-ray and gamma-ray energies through inverse Compton scattering. This creates a radiation environment that poses severe challenges for future interstellar travel. For human missions, the radiation exposure would be catastrophic without substantial shielding. Even at moderate velocities, a spacecraft moving through interstellar space would encounter radiation doses around 70 rems per year. Safe levels for humans range between 5 and 10 rems annually. At relativistic speeds, the situation deteriorates dramatically as oncoming interstellar hydrogen transforms into penetrating radiation. Voyager doesn't face these biological concerns, but radiation still affects its electronics. Cosmic ray impacts can flip bits in computer memory, corrupt data, or damage circuits. The spacecraft's design includes radiation hardening, but decades of exposure accumulate effects. Some redundant systems have failed after cosmic ray strikes. The spacecraft continues measuring this radiation environment. The cosmic ray detector counts particle impacts and measures their energies. This data reveals how cosmic ray intensity varies with position in interstellar space. The measurements show gradual increases in high-energy particle flux as Voyager moves farther from the Sun's protective influence. Interstellar space also contains dust particles, though they comprise only about 1% of the medium's mass. These grains consist of silicates, carbon, ice, and iron compounds. They're typically fractions of a micron across, roughly the wavelength of blue light. Despite their small size, dust particles profoundly affect astronomical observations. They scatter and absorb starlight, creating interstellar extinction that dims distant objects. The scattering preferentially affects shorter wavelengths, making stars appear redder than their actual colors. This reddening effect must be accounted for when measuring stellar properties. Dust also serves as the foundation for interstellar chemistry. Molecular clouds, the densest regions of interstellar space, can contain 10,000 molecules per cubic centimeter or more. These clouds enable chemical reactions impossible in the more dilute medium. Cosmic rays drive much of this chemistry. When high-energy particles ionize hydrogen and helium, they initiate reaction chains that produce increasingly complex molecules. Radio astronomy has discovered over 200 molecular species in interstellar space, with about 4 new ones identified each year. Some of these molecules are organic compounds relevant to biology. Polycyclic aromatic hydrocarbons subjected to interstellar conditions transform into more complex organics through hydrogenation, oxygenation, and hydroxylation. These processes represent steps toward amino acids and nucleotides, the building blocks of proteins and DNA. This chemistry occurs in regions Voyager will never reach. The spacecraft's trajectory doesn't pass through dense molecular clouds. It travels through relatively empty regions where particle densities remain low. But even in these sparse areas, the interstellar medium maintains subtle structure. Voyager's plasma wave instrument detects this structure through electron oscillations. The spacecraft has discovered a continuous hum of plasma waves, not just occasional bursts triggered by solar events. This persistent background reveals electron density variations as Voyager moves through different regions of local interstellar space. The measurements show density fluctuations over time. Since entering interstellar space, Voyager 1 has recorded density variations ranging across factors of 2 or 3. These changes reflect the medium's inhomogeneous nature. Even in regions far from stellar influence, the interstellar medium contains structure on scales ranging from astronomical units to light years. Beyond the local interstellar medium lies even more extreme emptiness. Intergalactic space contains roughly 1 atom per cubic meter, making it 1,000,000 times emptier than interstellar space. Yet this ultra-dilute plasma accounts for approximately half the ordinary matter in the universe. Voyager won't reach intergalactic space. The spacecraft will remain within the Milky Way's gravitational influence indefinitely. But its measurements of interstellar space provide the only direct sampling of conditions beyond the solar system's protective bubble. These measurements will continue for perhaps another decade before power limitations silence the instruments. When that happens, Voyager will become a passive object, still moving through interstellar space, but no longer reporting conditions. The spacecraft will pass other stars eventually. In roughly 40,000 years, Voyager 1 will drift within 2 light-years of the star Gliese 445. In roughly 300,000 years, Voyager 2 will approach Sirius to within 4 light-years. These close approaches happen purely by chance. The spacecraft weren't aimed at any particular destination. Even these close approaches represent vast distances. 2 light-years equals about 20 trillion kilometers. Voyager won't enter another star system. It will simply drift past, its trajectory bent slightly by gravitational influences, but continuing outward through the galaxy. The spacecraft's physical condition will deteriorate over cosmic timescales. Micrometeorite impacts will gradually erode surface features. Cosmic rays will damage materials at the atomic level. But these processes occur slowly. The spacecraft could remain recognizable for millions of years. The golden record provides the most durable component. Gold resists corrosion even in terrestrial environments. In the vacuum of space, with no oxygen or water, it should remain stable for billions of years. The record's grooves might survive longer than the spacecraft's structure. This longevity transforms Voyager into an unintentional time capsule. The spacecraft carries information about human civilization across cosmic distances and timescales that dwarf historical records. Clay tablets survive thousands of years. Stone monuments endure tens of thousands. Voyager could persist for billions. Whether anyone ever finds it remains unknowable. The probability seems vanishingly small. Space is vast, and Voyager is tiny. Even passing through regions with advanced civilizations, the spacecraft could drift unnoticed. But possibility exists, and that possibility elevates Voyager beyond its scientific mission. The spacecraft becomes a message, an assertion that we existed, that we wondered about the cosmos, that we reached beyond our planetary cradle. That message travels through an environment hostile to biological life, but navigable by machines. Interstellar space represents both barrier and medium. It isolates star systems across distances requiring thousands of years to traverse at chemical rocket speeds. Yet it permits passage for those patient enough to accept the journey. Voyager demonstrates this possibility. The spacecraft proves that human-made objects can survive interstellar space can function in that environment, can return information about conditions there. This knowledge informs future mission concepts. Interstellar probe designs now consider radiation hardening requirements based on Voyager's experience. They incorporate power systems capable of lasting decades. They plan for autonomous operation as communication delays stretch across light hours. These future missions might intentionally target nearby stars. They could carry instruments specifically designed to characterize interstellar medium properties. They might use advanced propulsion to reduce travel times from tens of thousands of years to hundreds. But even ambitious designs face the fundamental challenge Voyager encountered. Interstellar space is so vast that traversing it requires accepting timescales beyond human lifespans. The distances aren't just large, they're measured in units that humble imagination. Voyager's current distance of roughly 25 billion kilometers represents only about one light day. Light crosses this distance in 24 hours. Yet Voyager required over 4 decades to reach this distance. The nearest star beyond our Sun lies over 4 light-years away, more than 1,400 times farther. These scales make interstellar space both fascinating and forbidding. The environment between stars contains structure, complexity, and phenomena worth studying. But accessing that environment demands patience measured in generations. Voyager embodies this patience. The spacecraft was designed before anyone alive today was born. It continues operating after most of its creators have retired or died. It will drift through space long after everyone currently alive is gone. And through this persistence, it reveals interstellar space not as true emptiness, but as a medium with properties, structure, and significance. The space between stars shapes galactic evolution, enables stellar formation, and distributes elements throughout the cosmos. Understanding it matters for comprehending our place in the universe. Voyager provides humanity's first direct measurements of that environment. The data it returns, while the spacecraft's power lasts, represents knowledge impossible to obtain any other way. And after the transmitters fall silent, the spacecraft itself becomes a permanent artifact of human existence, drifting through the deadly emptiness we dared to explore. The measurements continue arriving. Each transmission carries data about conditions nobody anticipated, revealing complexities in what seemed simple emptiness. Voyager samples regions where electron density climbs unexpectedly, where magnetic fields twist in patterns that don't match theoretical predictions, where plasma waves resonate at frequencies indicating structure on scales nobody predicted. These discoveries reshape understanding. Before Voyager crossed the Heliopause, models treated interstellar space as relatively uniform. The spacecraft's measurements prove otherwise. The medium has texture, variation, boundaries between different conditions. What appears empty from Earth contains gradients, transitions, zones where properties shift across distances measured in astronomical units. Scientists analyzing this data face challenges their predecessors never encountered. The environment Voyager measures exists nowhere else we can study directly. Laboratory experiments can't recreate interstellar conditions. Telescopic observations provide indirect measurements. Voyager alone samples the medium itself, recording particle densities and field strengths and temperatures that theory predicted but couldn't confirm. Each data point requires interpretation against theoretical frameworks developed before anyone knew what interstellar space actually contained. Models assumed certain density ranges. Voyager found different values. Predictions suggested specific magnetic field orientations. Measurements revealed alternative configurations. The process of reconciling theory with observation advances understanding incrementally. But time pressures this work. Power output declines steadily. The plutonium-238 in Voyager's generators decays at a rate nobody can alter. Each year brings lower voltage, reduced capacity, fewer watts available for instruments and heaters and transmitters. Mission controllers manage this decline through careful rationing, shutting down non-essential systems, prioritizing measurements that provide unique value. The decisions grow harder as power drops. Which instruments deserve those remaining watts? The magnetometer measures fields that future missions traveling different paths won't replicate. The cosmic ray detector counts particles that vary with location and solar cycle phase. The plasma wave instrument detects oscillations nobody predicted. Each provides irreplaceable data. None can run indefinitely. Sometime in the next decade, power levels will fall below thresholds needed for any instrument operation. The spacecraft will still exist, still travel outward at 17 kilometers per second, but it will go silent. The stream of measurements will stop. Scientists will work with whatever data arrived before that final transmission. This creates urgency around analysis. Researchers search existing datasets for subtle patterns that might reveal phenomena not yet recognized. Machine learning algorithms scan years of measurements, flagging anomalies that human analysts might miss. Each potential discovery requires verification, distinguishing real signals from instrumental artifacts or random fluctuations. The work proceeds knowing that no new data will arrive forever after Voyager falls silent. Future interstellar missions might launch decades from now, but they'll sample different regions along different trajectories. Voyager's specific measurements of the local interstellar medium near the Heliopause during this particular epoch will never be duplicated. This uniqueness elevates each measurement's value. The data describes conditions during a specific moment in galactic time, at a specific location in space, under specific solar activity levels. All these factors vary. A century from now, the local interstellar medium might have different density as the solar system moves through regions with different properties. 1,000 years from now, supernova shockwaves might compress or heat the medium around what was once our neighborhood. Voyager captures one snapshot of an environment that changes, though slowly by human standards. The measurements preserve information about interstellar conditions during the early 21st century, for whatever future civilizations might analyze them. Meanwhile, the spacecraft continues its journey into regions increasingly isolated from solar influence. Each year carries Voyager deeper into the galaxy's disk, farther from the protective bubble of the heliosphere, into environments shaped purely by galactic processes rather than stellar ones. The radiation environment intensifies gradually. Cosmic ray counts climb as the sun's magnetic influence weakens with distance. High-energy particles from ancient supernovae bombard the spacecraft with increasing frequency. The cumulative exposure degrades materials, damages circuits, corrupts data storage. Yet Voyager persists. The engineering that went into its design, the redundancy built into its systems, the quality of 1970s aerospace construction continues proving itself. Components designed to last 5 years operate after 50. Systems expected to fail have survived. The spacecraft demonstrates remarkable resilience. This endurance matters beyond Voyager itself. Future interstellar probes will incorporate lessons learned from Voyager's longevity. Materials that survived will be selected for new missions. Design philosophies that proved successful will be replicated. The spacecraft serves as testbed for technologies needed for journeys not yet undertaken. But Voyager also reveals limits. The plutonium decay problem has no solution. Radiation damage accumulates irreversibly. Communication delays stretch as distance increases, making troubleshooting progressively harder. These challenges constrain what's achievable with current technology. Overcoming them requires advances we haven't made yet. Power systems lasting centuries instead of decades. Radiation shielding that doesn't add prohibitive mass. Communication protocols functioning across light-year distances. Autonomous systems capable of operating without human intervention for extended periods. Some concepts exist in theoretical form. Nuclear reactors could provide more power than radioisotope generators. Magnetic shielding might deflect cosmic rays. Laser communication could maintain bandwidth across vast distances. Artificial intelligence might enable autonomous decision-making. But translating concepts into operational spacecraft requires development efforts not yet funded. Voyager demonstrates what becomes possible when resources are committed to ambitious goals. The spacecraft exists because NASA invested in outer planet exploration during the 1970s. The mission continues because teams of engineers and scientists maintain operations despite budget constraints. The data returns because deep space network antennas track the signal across billions of kilometers. This infrastructure won't exist forever. The engineers who understand Voyager's systems will eventually retire. The scientists analyzing its data will move on to other projects. The antennas tracking its signal will be reallocated to newer missions. Institutional knowledge will fade, but the measurements will persist. Data archived in repositories will remain accessible to future researchers. The observations Voyager made will inform understanding long after the spacecraft itself falls silent. Scientific papers describing discoveries will be cited in contexts their authors never imagined. And somewhere in interstellar space, the physical spacecraft will continue its journey. Silent, inactive, but still moving outward through the galaxy at the velocity imparted by its final planetary encounter decades earlier. The golden record will remain attached, its grooves still encoding sounds and images from a civilization that might no longer exist when someone finally finds it. That possibility, however remote, changes what Voyager represents. The spacecraft transcends its scientific mission. It becomes humanity's ambassador to whatever lies beyond our solar system. It carries evidence of our existence into regions we cannot reach ourselves. The contents of that record reveal what we chose to share. Music from diverse cultures, greetings in dozens of languages, images showing human diversity, Earth's environments, our technological achievements. The selection process involved decisions about how to represent ourselves to unknown minds. Those decisions reflect assumptions about universality and communication. Mathematics was deemed universal because it describes relationships that should hold anywhere. Physical constants were included, assuming other civilizations would recognize them. Natural sounds represented Earth's acoustic environment. Human voices demonstrated our means of communication. But the record also contains choices that reveal our values, including multiple languages acknowledged cultural diversity. representing various musical traditions, showed appreciation for artistic expression. Images of people from different ethnicities reflected ideals about human equality. Future civilizations analyzing the record might recognize these choices, or they might interpret the contents differently than intended. Communication across species barriers involves uncertainties we can't resolve. We can only present what seems meaningful to us and hope some fraction translates. The engineering of the record itself demonstrates technological capability. The diagrams explaining playback show we understand physics and geometry. The choice of durable materials indicates we thought about preservation. The inclusion of a stylus and playing instructions reveals we considered practical usability. Whether anyone ever plays these records remains unknowable. The probability seems extraordinarily small. Space is vast. Voyager is tiny. Even if the spacecraft passes through regions inhabited by technological civilizations, it could drift unnoticed through their territory. But the record transforms Voyager's meaning regardless of discovery. The spacecraft becomes more than a scientific instrument. It represents an attempt to communicate across cosmic scales, to assert our existence to whatever might be listening, to preserve evidence of human civilization against timescales that dwarf recorded history. This symbolic dimension complements Voyager's scientific achievements. The measurements matter for understanding interstellar space. The message matters for understanding ourselves, for confronting questions about our place in the cosmos, about whether we're alone, about what we want to communicate if we're not. The space between stars contains hazards that would kill unprotected humans in seconds. Vacuum, radiation, temperature extremes, each independently lethal. Yet machines can navigate this environment. Voyager proves that spacecraft can survive interstellar space, can gather data there, can transmit discoveries across billions of kilometers. This knowledge enables future exploration. We now know what interstellar probes must withstand. We understand the radiation environment they'll encounter. We've measured the particle densities, magnetic field strengths, and plasma wave frequencies that characterize the local interstellar medium. Building on this foundation, future missions could carry more sophisticated instruments, travel faster through improved propulsion, last longer with advanced power systems. They could intentionally target nearby stars, arriving within human lifetimes rather than thousands of years. They could search for planets around those stars, analyze their atmospheres, look for signs of life. These possibilities require technological advances and sustained commitment, but they're not impossible. Voyager demonstrates that interstellar space, while hostile, is navigable. The barrier between solar systems isn't impenetrable, it's just vast. And that vastness contains structure worth studying. The interstellar medium shapes galactic evolution. It provides raw material for star formation. It distributes heavy elements synthesized in stellar cores. It hosts chemistry that might produce biological precursors. Understanding it matters for comprehending how galaxies function, how stars form, how the elements that make planets and life spread through space. Voyager's measurements address these questions through direct observation. The spacecraft samples the medium itself rather than observing it from Earth. This ground truth calibrates models and tests theories in ways remote sensing cannot. The data also reveals phenomena nobody anticipated. The continuous plasma oscillations, the higher than expected electron densities, the magnetic field orientations that differed from predictions. These surprises demonstrate the value of direct exploration versus theoretical speculation. Science advances through this interplay between prediction and measurement. Models suggest what should exist. Observations reveal what actually exists. The discrepancies drive understanding forward, forcing refinement of theories, suggesting new questions, opening research directions nobody considered. Voyager's contribution to this process will extend beyond its operational lifetime. The datasets it generated will be analyzed for decades. Future researchers will apply new techniques to old data, finding patterns that weren't apparent initially. The measurements will be compared with observations from later missions traveling different paths, revealing how interstellar conditions vary with location and time. But eventually, the spacecraft itself becomes more artifact than active explorer. When its transmitters fall silent, when its instruments stop recording, Voyager transitions from functional probe to passive monument. It continues traveling, but it stops contributing new knowledge. This transition doesn't diminish what Voyager achieved. The spacecraft fulfilled its mission beyond any reasonable expectation. Designed for a 5-year tour of Jupiter and Saturn, it operated for 50 years and reached interstellar space. It discovered moons, rings, and atmospheric phenomena around the outer planets. It provided the first images of Uranus and Neptune. It crossed the Heliopause and measured conditions beyond. Each achievement resulted from engineering excellence, operational skill, and institutional commitment. The spacecraft worked because thousands of people designed it carefully, tested it thoroughly, and operated it competently. The mission succeeded because NASA maintained support despite budget pressures, because engineers solved problems as they arose, because scientists extracted maximum value from the data. This collaborative achievement demonstrates what becomes possible when organizations focus sustained effort on ambitious goals. Voyager exists because people chose to build it, to launch it, to maintain it across decades. The mission continues because institutions preserve the expertise and infrastructure needed to operate aging spacecraft across interstellar distances. Future generations will face similar choices. Will they maintain contact with Voyager as long as possible? Will they fund new interstellar missions? Will they preserve the knowledge gained from humanity's first ventures beyond the heliosphere? These decisions will shape what we learn about the universe and our place in it. Interstellar space contains information accessible only through direct measurement. Theoretical models help, but they can't replace actual observations. Understanding the galaxy requires going there, sampling conditions, recording data, transmitting discoveries. Voyager began this process. The spacecraft provided our first measurements of true interstellar space. It revealed the medium's complexity, its structure, its hazards. It demonstrated that machines can survive that environment and return useful data. Building on this foundation, future missions could extend humanity's reach farther into the galaxy. They could map interstellar space more thoroughly, sample different regions, measure how conditions vary across distance and direction. They could search for other planetary systems, analyze their properties, look for signs of habitability or life. These explorations would take generations. Interstellar distances don't yield to impatience. The spacecraft traveling to nearby stars would require decades or centuries to arrive. The people who design such missions won't live to see their success. The data they return will be analyzed by researchers not yet born. This intergenerational character defines deep space exploration. Individual careers span decades, missions span lifetimes, scientific programs span centuries. Success requires accepting timescales that exceed human experience. Voyager embodies this patience. The spacecraft was designed before anyone alive today was born. It continues operating after most of its creators have died. It will drift through space long after everyone currently living is gone. And through this persistence across generations, it reveals knowledge about the universe that wasn't accessible any other way. The deadly emptiness between stars turns out to contain structure, variation, and complexity nobody fully anticipated. What seemed like simple vacuum proves to be a medium with multiple phases, chemical activity, and properties that vary with location. Understanding this environment required going there, measuring conditions directly, transmitting data across billions of kilometers. That understanding continues accumulating as Voyager travels deeper into interstellar space, each measurement adding detail to humanity's map of the galaxy's structure. The process will continue until power fails and transmissions cease. Then the spacecraft will coast silently through the void, carrying its golden record toward encounters with other stars thousands of years from now. But the knowledge Voyager generated persists. The measurements exist in archives. The discoveries appear in scientific literature. The techniques developed for the mission inform future efforts. The spacecraft's legacy extends beyond its operational lifetime, shaping how we understand the space between stars and how we approach exploring it. This is what becomes possible when we venture into the deadly emptiness beyond our solar system. Not instant answers, but patient accumulation of knowledge. Not simple confirmation of theories, but surprising discoveries that demand explanation. Not conquest of space, but careful exploration of an environment that will outlast our entire civilization. Voyager continues that exploration, traveling ever outward, measuring what exists in the vast darkness between the stars.